Section: Introduction and Related Work. In this section, we explore the intriguing puzzle of generative AI, particularly how it generates seemingly endless and creative outputs. We aim to understand the source of this creativity and how it arises from a limited training set. Our focus is on convolutional diffusion models for images, where we present the first analytical and interpretable theory that can predict their outputs on a case-by-case basis. We explain that these models create images from locally consistent patch mosaics derived from the training data. Denoising diffusion probabilistic models, DDPMs, were introduced in earlier works and later unified with score matching techniques. We primarily utilize denoising diffusion implicit models, DDIMs, in our study. Diffusion models are now significant not only for image generation but also for video generation, drug design, protein folding, and text generation. These models learn to reverse a forward diffusion process that transforms the training set distribution into a Gaussian noise distribution, using a time-dependent mixture of Gaussians centered around the data points. The challenge lies in the creativity of diffusion models. If they perfectly learn the ideal score function, they would only reproduce the training examples, not generate new ones. Thus, their creativity stems from their inability to achieve this ideal score function. We question how they can fail in ways that still produce sensible new examples that differ from the training set. Various studies have examined the properties of diffusion models, some assuming they learn the ideal score function accurately or with minor errors. Others have established accuracy guarantees under different assumptions about the data distribution and function classes. However, assuming that diffusion models learn the ideal score function limits their ability to generate new examples, as they would only reproduce what they memorized. Notably, these models can combine aspects of their training data in many novel ways, prompting investigations into the mechanisms behind their generalization. We identify two key biases that prevent convolutional diffusion models from learning the ideal score function: translational equivariance from parameter sharing in convolutional layers and locality due to the model's limited receptive field size. We demonstrate that these biases are sufficient to explain the creative outputs of these models. Our analysis also shows similarities to early patch-based texture synthesis methods. Our contributions include reviewing why models that learn the ideal score function can only memorize, deriving minimum mean squared error approximations to the ideal score function under various constraints, and finding simple analytical solutions. We introduce a boundary-broken equivariant local score machine, which provides an interpretable theory for transforming noise into creative images without explicit training. We characterize the samples generated by this machine, showing how it achieves creativity through locally consistent patch mosaics from different training set images. Our boundary-broken else machine is not only interpretable but also predictive, achieving high agreement with outputs from trained UNets and ResNets on various datasets. Our comparison between theory and experiment reveals that trained diffusion models generate spatial structures progressively and use image boundaries to guide the generation process. We also explain the tendency of diffusion models to produce spatially inconsistent images at fine scales, linking this to excessive locality in the reverse generative process. Finally, we compare our local else machine theory to more advanced UNet architectures with non-local self-attention layers, finding that our local theory can still partially predict their outputs while highlighting the role of attention in creating coherent objects from local patch mosaics. Overall, our work sheds light on the mechanisms of creativity in convolutional diffusion models and lays the groundwork for studying more advanced attention-enabled models. Section Summary. In this section, we explore the creativity of convolutional diffusion models, revealing that their ability to generate novel outputs stems from their failure to perfectly learn the ideal score function, which leads to the formation of locally consistent patch mosaics from training data. We derive an interpretable theory that quantitatively predicts individual outputs, demonstrating how two inductive biases, translational equivariance and locality, contribute to this creative process. Section: The ideal score machine only memorizes. In this section, we discuss how the ideal score machine functions solely by memorization. We begin by explaining that any diffusion model learning the ideal score function from a limited dataset can only memorize that data. The core concept of diffusion models involves reversing a random forward diffusion process that gradually transforms the data distribution into a series of distributions over time. This process ultimately leads to a final distribution that resembles a standard Gaussian distribution. During the forward diffusion, data points are drawn closer to the origin while Gaussian noise is added. When we focus on a specific data point, the conditional probability becomes a Gaussian distribution centered around a shrunk version of that point, with increasing variance over time. As time progresses, the mean of this distribution shrinks, while its variance grows, until it resembles a standard Gaussian for all initial points. To reverse this process, we can sample from the final Gaussian distribution and then trace it back in time using a deterministic flow based on the score function of the distribution. This flow creates a series of reverse distributions that perfectly undo the forward process. The reversal happens because, for any finite dataset, the distribution is a mixture of Gaussians centered at the shrunken data points, and the score function directs the samples back toward these points. We then explore what occurs when our estimate of the score function matches the ideal score function for any finite dataset. In this case, the score of the Gaussian mixture acts as a force pulling the sample toward the shrunken data points, weighted by the probability that the sample originated from those points. This dynamic can be viewed as a Bayesian guessing game, where the current sample optimally infers its origin and flows toward the corresponding shrunken data point. Crucially, since the reverse flow accurately reverses the forward diffusion, the resulting distribution matches the empirical data distribution, indicating that the ideal score machine effectively memorizes the training data. We explain that this memorization occurs due to positive feedback instabilities in the reverse flow. The closer a sample is to a shrunken data point, the stronger the belief that it originated from that point, which in turn reinforces the force pulling it closer. This feedback loop causes the belief distribution to quickly concentrate on a single data point, leading the sample to flow toward that point. Thus, we conclude that any diffusion model learning the true score on a finite dataset must memorize the training data and cannot generate new samples that are significantly different from it. This memorization phenomenon, while intuitively explained through the ideal score machine, has been well documented in previous research. Section Summary. In this section, we explain that any diffusion model learning the ideal score function on a finite dataset will only memorize the training data rather than generate new samples. This occurs because the reverse flow process reinforces the belief that a sample originated from a specific data point, leading to a concentration of samples around the training data rather than creative generation. Section: Equivariant and Local Score Machines. In this section, we discuss the limitations of the ideal score machine in terms of creativity, which makes it unsuitable for modeling realistic diffusion processes beyond simple memorization. To address this, we aim to identify straightforward inductive biases that prevent the ideal score function from being learned on a limited dataset. By doing so, we hope to develop a new understanding of how diffusion models can creatively generate samples that differ significantly from the training data. We observe that many diffusion models utilize convolutional neural networks, CNNs, to estimate the score function. These CNNs exhibit two main inductive biases: translational equivariance and locality. Translational equivariance means that if we shift the input image, the output from the CNN will shift in the same way. More broadly, networks can be equivariant to various symmetry groups. Locality refers to the fact that CNN outputs depend only on a small area of neighboring pixels, due to the limited range of convolutional filters. We aim to find an optimal estimate of the ideal score while adhering to these locality and equivariance constraints. We start by defining these concepts formally. We denote a model score function as m_t, which takes an input image and produces an estimated score. A model is considered equivariant if translating the input image results in a corresponding translation of the output score. For images, we define the spatial translation group as the set of all possible shifts in two dimensions. If we apply periodic boundary conditions, CNNs maintain this translational equivariance. However, using zero padding at the image edges disrupts this property, and we will extend our theory to account for this scenario. Next, we define locality in the context of image data. For a given pixel location, the model score function at that pixel should depend only on the pixel values in its immediate neighborhood. This means that the score for a pixel does not rely on values from distant pixels, ensuring that decisions about pixel flow are made independently based on local information. We then explore the optimal minimum mean squared error (MMSE) approximation to the ideal score function under these constraints. While we provide detailed derivations elsewhere, the key results are straightforward. First, we consider the case of equivariance without locality. The MMSE equivariant approximation to the ideal score is similar in structure to the ideal score, but the dataset is expanded to include all possible translations of the original dataset. This leads us to the equivariant score S machine. Unlike the ideal score machine, which simply memorizes the training data, the S machine can only generate translations of the training images, demonstrating limited creativity. Section Summary. In this section, we explore the limitations of ideal score machines in modeling realistic diffusion processes and propose incorporating inductive biases of equivariance and locality to improve creativity in sample generation. By defining these biases and deriving an optimal score estimate, we introduce the equivariant score S machine, which, while still limited to generating translations of training images, represents a step towards understanding the creative capabilities of diffusion models. Section: The Local Score (LS) Machine. In this section, we discuss the local score (LS) machine, where we introduce locality without requiring equivariance. The minimum mean square error local approximation to our score function is derived from the local terms, which pull the pixel value towards a modified training set pixel value. However, instead of using a global belief that applies to all pixels, we now use a local belief that depends on the specific pixel location. This local belief reflects the probability that a sample image at a certain time originated from a training image, based only on the local neighborhood around that pixel. The closer the local image patch is to the corresponding training image patch, the stronger this belief becomes. By replacing the ideal score with this local score, we create the LS machine, which can exhibit significant creativity by allowing different local image neighborhoods to interact with various training image patches. This means that even though the local beliefs concentrate on specific training images, those images can differ for distant pixels, leading to a rich variety of outputs. However, a limitation of the LS machine is that a local image patch can only flow towards a training patch from the same location. Next, we explore the equivariant local score (ELSE) machine, which addresses this limitation. By imposing equivariance, we allow any local image patch to flow towards any training image patch, regardless of their locations. This is similar to how the ELSE machine generates images that can be globally translated. We assume that all local neighborhoods have the same shape, which we can visualize as a square patch of pixels. In the ELSE machine, the optimal approximation to the ideal score now allows for a broader range of training patches to influence the flow for each pixel. Each pixel must track a larger belief state regarding which local training patch, from any location, originated from its local image patch. Essentially, this means that each pixel loses specific knowledge of its location and must guess both the training image and its location within that image. Overall, the ELSE machine enables us to creatively generate a vast number of novel images by combining local training patches from various locations and placing them anywhere in the generated image. We refer to this approach as a patch mosaic model of creativity. Section Summary. In this section, we introduce the local score (LS) machine, which allows local image patches to draw from different training images, enhancing creativity while maintaining locality constraints. We then extend this concept to the equivariant local score (ELSE) machine, enabling any local patch to flow towards training patches from any location, thereby significantly increasing the model's creative potential through a patch mosaic approach. Section: Breaking equivariance through boundaries. In this section, we discuss how boundaries affect translational equivariance in convolutional neural networks, CNNs. When we use zero padding at the edges of images, we inadvertently disrupt exact translational equivariance. We can adjust our else machine to accommodate this disruption, as detailed in the appendix. The main idea is that this broken equivariance allows each pixel to gain some awareness of its position within the image. For instance, if the local image patch around a pixel contains many zero values, the pixel can deduce its location relative to the boundary and use this information in the process of generating samples. Essentially, the local patch should only connect to training patches that match the observed zero padding pattern. This means that patches from the interior, edges, and corners of images will only connect to similar training patches that have the same boundary characteristics. We also explore what happens at the end of the reverse process in our models, particularly when they generate new samples that differ from the training data. We prove a theorem that describes the samples produced by the ls, else, and boundary-broken else machines. This theorem states that if certain limits exist, then for every pixel, the generated value will match the central pixel of the closest local training patch. This means that the generated samples are locally consistent, adhering to three conditions. Each pixel corresponds uniquely to a training patch, the pixel value matches the central pixel of that patch, and the rest of the generated patch resembles the training patch more than any other. To illustrate this concept, we consider a simple example with a training set of just two images, one completely black and one completely white. A diffusion model trained on these images would only produce those two images. However, an ls or else machine can create many new samples that are locally consistent patch mosaics, where each pixel is either black or white, reflecting its assignment to the corresponding training patch. The local consistency in this case simplifies to the rule that the majority color in any local patch must match the color of its central pixel. Next, we test our theory using two CNN architectures, a standard UNet and a ResNet, trained on three datasets, MNIST, Fashion MNIST, and CIFAR10. We focus on these simpler datasets because our theory specifically applies to CNN-based diffusion models, while more complex models are needed for more intricate datasets. Finally, we examine how the size of the local patch changes over time during the reverse flow. We find that the locality scale shifts from larger to smaller as time progresses. Therefore, we treat the size of the local patch as a dynamic variable, calibrating it to the UNet and ResNet models. Section Summary. In this section, we discuss how CNNs break translational equivariance due to zero padding, and we propose modifications to our else machine to account for this by allowing pixels to infer their location relative to boundaries, thus generating locally consistent samples. We also present a theorem characterizing the creative outcomes of our models, demonstrating that they produce locally consistent patch mosaics, and we validate our theory through experiments on CNN architectures trained on simple datasets. Section: Theory predicts trained outputs case by case. In this section, we compare the outputs of our scale-calibrated boundary-broken else machine with those of ResNet and UNet on a case-by-case basis, using the same initial noise samples. We observe an excellent match between the outputs and the theoretical predictions. Specifically, we find strong quantitative agreement between the CNN outputs and the else machine outputs. For ResNets, the median correlation values between theory and experiment are 0.94 for MNIST, 0.90 for Fashion MNIST, and 0.90 for CIFAR10. For UNets, the median values are 0.84 for MNIST, 0.91 for Fashion MNIST, and 0.82 for CIFAR10. This level of accuracy in explaining the outputs of a trained neural network generative model is unprecedented. Notably, the else machine outperforms the is machine in explaining all trained outputs. We also trained circularly padded ResNets on MNIST and CIFAR10, finding a good match between the non-boundary broken else machine and experimental results. Interestingly, circular padding leads to more texture-like outputs rather than localized digit-like outputs, highlighting the importance of boundaries in anchoring diffusion models, particularly for MNIST. We note that diffusion models often produce spatially inconsistent images, such as incorrect numbers of fingers or limbs. Our trained models on fashion MNIST exhibit similar inconsistencies, like pants with too many or too few legs. Our theory, which aligns with the outputs on a case-by-case basis, also reproduces these inconsistencies. We explain that these arise from excessive locality at late stages of the reverse flow, where different parts of the image must decide on their form without knowing the total number of limbs, leading to errors. While our local theory accurately explains CNN-based diffusion model outputs, many models incorporate non-local self-attention (SAW) layers, which challenge our local assumptions. To explore this, we compare our else machine theory with outputs from a U-Net plus SAW model pre-trained on CIFAR10. Remarkably, our else model predicts the U-Net plus SAW outputs with a median correlation of about 0.75, significantly higher than the baseline is machine's median of 0.47. The outputs from the U-Net plus SAW model can be categorized into three classes. 1. Semantically incoherent images resembling else predictions. 2. Semantically coherent images with some correlation to else outputs but little resemblance. And 3. Semantically coherent images that closely resemble the less coherent else outputs. The third class is the most prevalent and intriguing, as the U-Net plus SAW seems to extract coherent objects from the else patch mosaic while enhancing the background. Overall, while our findings indicate that the else theory shares both quantitative and qualitative similarities with U-Net plus SAW outputs, a comprehensive theory on the role of attention in the creativity of diffusion models is still needed. However, the observed correspondences suggest that the else theory lays a crucial foundation for future exploration in this area. Section Summary. In this section, we demonstrate that our scale-calibrated boundary-broken else machine closely matches the outputs of ResNet and U-Net models across various datasets, achieving high median R-squared values, which indicates a strong alignment between theory and trained model outputs. We also explore the impact of boundary conditions on diffusion models, identify spatial inconsistencies in generated images, and find that our local theory can predict outputs from non-local U-Net plus SAW models, suggesting a foundational link between our theory and the behavior of attention mechanisms in diffusion models. Section. Discussion. Sure. Please provide the text you would like me to paraphrase and simplify.